Hey everybody, I hope you're having an awesome semester. I just wanted to post this video walkthrough of the first lab that we assigned for AI Campus. Again, these are not due back to us. You don't have to complete these and turn these into anyone. You may be discussing these with your team in your weekly meetings. These are really just designed to provide some foundational skills and teach you some of the underlying concepts behind commonly used packages and techniques in machine learning. So it's really easy sometimes if you're starting to learn coding and machine learning, programming in Python, you find these online tutorials and you just start blazing through the tutorial. And next thing you know, you've done some type of work or some type of project, but you may not understand the mathematical frameworks or the underlying concepts of whatever you did. And in order to build long-term skills that are sustainable, that you can apply to different scientific challenges, you really need to have that foundational knowledge. And so that's what these labs are all about. Some of these labs were designed for a summer class that I took with Dr. Jonathan Stubblefield, who's coaching the Zelda game team. And he taught a class over the summer called Algorithmic Techniques and Foundations. Some of these are labs that other faculty have put together for me for summer programming in the past, and some are labs that I have come up with for summer programming. So they're from a variety of sources, and we always try to use data sets that are not used in the common tutorials. You're not going to find, we're not going to give you any labs using the iris data set or anything like that. We try to make it interesting and new and, attainable. So I hope that you guys enjoy them. And without further ado, I will dive into this first lab on linear regression. This is the guide, which I have for the mentors and coaches, and then that I posted in Slack recently. And then we also had the level 1 lab and the level 2 lab. And just as a quick reminder, the level 1 is designed for beginners or people that don't have a lot of experience. And the level 2 is with like most of the code missing, and that's for people that have more experience. So it starts out with just some basic information about the lab. This is one that was developed by Dr. Stubblefield for the summer class that I took last summer. And it has our legend in here. So for those of you who are not super familiar with Colab, you're going to run each cell by clicking the little play button on the cell. So if you're working in Google Colab, you probably will need to install this package. So we'll go ahead and run this first cell, and this will also connect to the runtime and get our session started. It'll take just a minute to get that to load. All right. So now on this one, we're going to import the packages that we're going to use in the lab, probably more than we really need. All right. So for the linear regression, this lab was utilizing the California housing data set, which is provided by scikit-learn. They have a bunch of data sets that you can use that are built in, and that they have tutorials to support. So first, what we're going to do is import the data set, and then we're going to compare a few different linear regression techniques to try to help you understand the different approaches and tools that are available. So first, it says we're going to fetch the California housing data set. Then we're going to calculate a linear regression line using only NumPy and SciPy functions. And then create a scatter plot with the selected predictor. So we'll get to choose which predictor we want to use, calculate and print the R² score. And then we'll perform the scikit-learn built-in linear regression function on the same data and compare the results. I'm not super familiar or experienced with the fetch command for the scikit-learn data sets. This was something I just recently learned for this lab, actually. So there's a little kind of weird thing I noticed about it that I don't really know how to explain. So maybe somebody can chime in on that for me later. But basically, this first command will pull in the data set and assign it to this variable house. I included some supplemental information in here about that, how to fetch data from scikit-learn that I pulled from the documentation online. So in machine learning, it's really common to use these terms interchangeably, but basically the response is also the y variable or the dependent variable or the target. And then the feature names. So that's going to be a list of all of the feature names, and feature is kind of used interchangeably to describe all of the columns in a data set, or attributes, or predictors, the X variables or the independent variables. Those can all kind of be used interchangeably. Okay, so the first step is to identify the X and Y variables that we're going to use, or the predictors and the response. Okay, the first thing we're going to do is use the print command and print the information about the target attribute that's described here, that gives us what the response or Y or dependent variable is going to be. So we can just go ahead and print that and see what it is. Okay, so it's telling us here, it's showing us the head and tail of the response column, the Y column, and it gives us the name that it's called here. So this is the feature name. It's called med house val. I'm assuming it stands for median house value. It has 20,640 observations. So it starts with 0 and goes to 20,639. And it tells us that the data type is a float 64. So that's the characteristic of the actual data that's in this column, instead of like an integer or a string or something like that. All right. We want to look at the first few rows of the data set. So this is that little kind of weird thing that I noticed. I didn't know why this happened, but I just learned as I was working through this that I had to redo this fetch command, but add this parameter here for frame to convert it into a pandas data frame. So again, if somebody knows why that is the case, I would love to find out, but I just figured it out as I was doing this lab. So basically we're gonna use the fetch command again, add this additional parameter, and we'll write a print statement to use the header function, which will give us the first few rows of the data. All right, so this is what the data looks like. So we have columns here. We have med inc. I don't know if that's income or something, house age, probably in years, average rooms, average bedrooms. I'm assuming this is the average number of rooms in the house, the average number of bedrooms, population. I don't know exactly what that is. I'm sure it's in the data dictionary. Average occupancy, the latitude and longitude, which would give us an idea of where the house is located, and then the target, which is the median house value. So just looking at the data, part of your initial kind of exploratory data analysis is often just really looking at these observations. And so if this is the target, I'm looking here at the value column, and I notice that the first row has a higher value, so 4.526, and it basically decreases slowly as we go down. So now we're going down to 3.58, 3.52, 3.41, 3.42. So it's not exactly consistently decreasing, but it is generally going down. So just looking at the other features, I was looking to see which ones also are kind of generally going down. Now, the latitude and longitude information does not change much over these few observations. The occupancy, I don't think would fit this bill because it starts at 2.5 and it kind of goes up to 2.8 and then back down to 2.1. Population, I also don't think. Average number of bedrooms, average number of rooms, none of these other variables are really matching the same kind of pattern just right off the bat, except for this one. So I don't know if this is income again. I can't remember what exactly that stands for, but this one looks like it might be kind of similar. So it starts with a higher number, 8.32, and it kind of generally goes down to like 3.8. So that's the one that I chose in the rest of my code on this, but some of you may have chosen other features, which is totally fine. So we'll just go ahead and move forward with the med inc, whatever that is, and see what the relationship is like with that and our target or our response, which is the house value. So now we'll assign the X and Y values from this data set. And I just use kind of a shorthand, kind of HY and HX to stand for house Y or house X. You can use whatever naming convention or nomenclature, whatever that you're comfortable with. Okay, so now we've got our X and Y stored. And the first thing is we are going to generate a scatter plot. This is a really important first step when you're doing exploratory data analysis, is to generate some initial visualizations. Oftentimes this can help jog your creativity and help you figure out a good, next steps and initial relationships between data. So to make a simple scatter plot, we're going to use matplotlib, which we've imported in shorthand as PLT. And we are going to customize it a little bit. So I included some information in here about the plot style, plotting symbol, and colors and stuff, which you can find in the style guide, which is linked in the references cell at the bottom of this lab. So I used B**, and that stands for blue star. So I'm going to generate a scatter plot with the plotting symbol as a blue star. And we're going to label the y-axis with our target name and the x-axis with our predictor name. And then we will tell it the command that we need to actually show the plot. So let's go ahead and run this. So this is interesting. We have kind of like a hard line here of, I guess, houses that have high value. And then we have this just kind of big cluster here. And I guess you could kind of see it might have some type of relationship. It does look like there is some level of cohesion here with just a few outliers. So let's proceed with the lab. So in Python, we have a couple of different options to do our linear regression. So the assignment was to do it manually with only SciPy or NumPy functions. And then we can also use, SciPy has a built-in a linear regression algorithm called linregress. And then we will compare the results to the scikit-learn linear regression package. So first, we're going to do it with the SciPy functions using standard deviation and stuff. We are taking you to algebra class for a second, and we are going to remind ourselves of the basic formula for a line, y equals mx plus b. So for fitting a regression line, this is basically the formula that we're going for. In the traditional formula of this, m would be the slope of the line, and b is the y-intercept. For the lab, we are going to reword this with some different terminology, and we're just going to say y equals bx plus a. Sorry to make that confusing for everybody, but I promise it's going to be easier in the long run. And basically, the slope is going to be the correlation coefficient, which is going to be a calculation we'll do. And then the y-intercept is also going to be a calculation of the relationship of the mean of y and the mean of b. Or of x. Okay, so we will need to calculate a few things in order to plug them into our line formula here to get the regression line. So the first thing we're going to do is calculate the Pearson correlation coefficient. This is a number that measures the linear relationship between two data sets. So this is really the heart of our linear regression formula. And basically, if you get something close to 0 or 0, that means there is no correlation between the data. And as the value approaches 1, that will indicate that there is a strong positive correlation. If it goes negative and approaching -1, that means there is a strong negative correlation. So I'll show you this on the plot when we generate this in a little bit. If you want to learn more about the Pearson correlation coefficient and the Pearson R function of SciPy, you can check the documentation, which is linked in the references cell at the end of the notebook. So first, we're going to use the Pearson R function to calculate the correlation coefficient and Pearson coefficient. And so basically what we'll do here is give it a command using the SciPy stats Pearson R function on our x and y variables, hx and hy. And it's going to return a tuple, which is 2 numbers. It's just a data type that has 2 numbers in it with the Pearson correlation coefficient and the p-value. So the output here, because our value is 0.68, so it's definitely higher than 0.5. If 0 means no correlation and 1 means like a strong correlation, I would say that anything over like a 0.5 is probably pretty good because that means there is some type of correlation there. So that's pretty good. and a p-value of 0.0. Who remembers what p-value, what is a significant p-value? So if you, again, taking it back to stats class or whatever, a p-value of under 0.05 is what you're looking for. So that means that the result is statistically significant. So I'm just going to copy and paste this number here and assign that to my CC variable, to calculate the correlation coefficient in a little bit. We'll use this in our calculation. So we'll just go ahead and assign that here. And then we are going to assign some variables to help us calculate the other terms that we're going to need for this line formula. So if we go back up to our math here, this is going to be how we get the A and B that we will plug into this formula. So first we need to calculate these, then we will plug them into our line formula here. So to get B, we need the Pearson R, which we just got, and then we also need the standard deviation of Y and X. So that's what we're doing here, SDX for standard deviation of X, SDY for standard deviation of Y. And we're just using some built-in NumPy functions here, which we've abbreviated as NP. And then we'll also use the built-in NumPy function for mean to calculate the mean of Y and the mean of X. So after we have these, we will be able to plug these variables in to this formula to calculate B, which is going to be our slope. So B is going to be the Pearson coefficient times the standard deviation of Y over the standard deviation of X. And then we will type B just to print B. We'll see what it is. Okay, so here's B is 0.4179, blah, blah, blah. To calculate A, we're going to need the means here, and that is going to be the mean of Y minus B times the mean of X. And so again, this is the formula that's up here in the notes, and we're going to go ahead and run that and store A. So A is 0.4508, blah, blah, blah. So now we have all of the components that we need for the formula of the regression line. And so what we're going to do is give PyPlot two kind of endpoints so we can generate the regression line on our scatter plot. So it really will look best if it starts on the y-axis, and which would be x equals 0, and ends near the highest x value where the data ends. And so if we go back up to our scatter plot, I think 14 or 15 would probably be a good target here. So let's go with like 14, I guess. So we're going to say x1 is 0 and x2 is 14. Our y-intercept is A. So we can copy that in. That's y1, and then we need to calculate the y2. So basically to draw a line, we just need two endpoints, right? So x1, x2, y1, and y2. So we'll calculate y2 by plugging these values into the formula for the line. And so we've got y, the formula for the line again is y equals bx plus a. And so we've got y2 equals b x2 plus a. And so if we rerun our plot, and this is the same code from earlier, except I'm adding something here. I've got a line in here to plot the regression line with our x1, our x2, our y1, and y2. I'm going to make it red, and I'm telling it that I want the line width to be 2, so it'll be nice and it'll stand out against the blue stars of the plot. So let's run this and see what it looks like. Okay, so we have our plot here that looks pretty nice. We definitely have a clear regression line here that shows some type of relationship perhaps. Now we are going to do the same thing with SciPy's built-in linear regression algorithm, which is called LinRegress. So all this needs is the X and Y parameters, and it's going to return 5 values. And those are the slope, the intercept, the R-squared score, the p-value, and the standard error. And so the p-value, again, we want it to be low, as close to 0 as possible. And we will have our slope and y-intercept, or our b and a values that we can plug into our regression line formula. So let's go ahead and run this. We can assign the values straight into, as we call the formula. So we did B for the B value, A for the A value, R for R value for R squared, P value for P value, and this for standard error. And all we have to pass it are the HX and HY arguments. And we will go ahead and print what those values are to see how it compares to our manually calculated numbers. We got A is 0.450855. A is 0.450855. Yep, B is 0.417938. 0.471938 is the same. All right. The R squared score, again, we got the 0.688. That's the Pearson coefficient that we calculated earlier, and it's the same number. Okay, so now we are going to test the built-in linear regression function in scikit-learn. You don't have to give it a lot of arguments, but if you want to look at the documentation, it does accept several arguments. It's a pretty flexible function or package. And basically, we're going to fit this in the same way that you will fit almost any type of regression or classification model that you're going to be using in scikit-learn. The only thing is scikit-learn can get picky about the shape of the X or the predictor feature. And so a lot of times you might find yourself reshaping your X variable into a one-dimensional array. So first we're going to convert the HX variable into an array and reshape it so that we can get the linear regression to work properly. And then we will assign it to a variable that we're just going to call REG for regression. All you need to do is type linear regression, and the spelling matters here, capitalization matters here, open and close parentheses, dot fit, and that's the standard syntax for fitting a model to some data. And we're going to fit it to our new X variable that we just assigned and reshaped, and then we're going to use our HY, the target or response variable that we were using before. And then we can print the regression score, and we can also print the intercept and the coefficient and compare the numbers. Okay. So right off the bat, the regression score, this looks very different than the R squared value. So these are two different metrics, and you can read more about these in the documentation that's linked in the references. But it does look like the coefficient and the intercept are, if not the same, pretty close. So we are going to make another plot, and we'll overlay both lines, the one that we calculated and then the one from the scikit-learn method. And so in order to do that, we are going to have to calculate a new endpoint, again, using y equals mx plus b. So here's the one that we did, the first ones that we calculated. And then we're going to plug in the same x1 and x2 variable or values to calculate a y2 for the scikit-learn. And so again, y equals bx plus a. We've got our intercept and our coefficient stored as variables. They're attributes of this regression model. So we can plug those in straight to the formula here. So y4 equals this variable is the coefficient times x2, 14, plus the intercept. And then we will generate the plot again. And we're going to make the plot, I'm going to change it and make the red line a little bit thicker. And then we will overlay a green line that's a little bit thinner in case they overlap a little bit so that we can see everything clearly. So let's go ahead and run this. There we go. All right, so yeah, they are overlaid. So it looks like there's the red line going up here, and then there's a green line just right on top of it. All the values are the same. So that's pretty good. So here's the references. I've linked all the documentation here. I highly recommend, if you're interested in learning more, that you go through and read some of these. The documentation is always a good place to find information and learn more about these packages and the different parameters that you can give to functions. So that's the first lab.